formula. So using this formula we can solve the JAM, NEET and other relevant questions which are asked in the competitive exams. So let us begin our session. So the first law is the Ohm's law, where V equal to IR, where V is the voltage, I is the current, R is the resistance. So this one we use for both the metallic conductors as well as the electrolytic conductors. So in electrochemistry basically we classify the conductors based on the conductivity, namely conductors, insulators and semiconductors. So conductors are further classified into two types. They are electronic conductors and electrolytic conductors. So our point of interest in the electrochemistry is the electrolytic conductors mainly. They also obey the Ohm's law. Okay, so this resistance is directly proportional to L and inversely proportional to A. So for metallic conductors, where L is the length of the wire, A is the cross-sectional area of the wire. But in the case of electrolytic conductor, L is the distance between the two electrode, A is the cross-sectional area of the electrode, because we deal with the electrode and electrolyte in the electrolytic conductors. So this is directly proportional. So in order to make it equal, we put the proportionality constant, that is known as the rho. Rho is R equal to rho into L by A, where R is the resistance, rho is the specific resistance, L is the distance between the two electrode, A is the cross-sectional area of the electrode. Together this L by A is known as the cell constant. Okay, so this is the first formula from the Ohm's law. We get this one, and correspondingly we know that the inverse of the resistance is known as the conductance. So I just put the symbol G as the conductance. G is the 1 by resistance. Similarly, I know the specific resistance. If I want to get the specific conductance, so I have to take the inverse of rho. So where rho is the specific resistance, so we get the corresponding quantities known as the specific conductance. So let me write all the quantities, where G is the conductance, R is the resistance that I have written already, rho is the specific resistance, kappa is the specific conductance. Okay, so as I know the kappa, so I can substitute this rho and rearrange this equation, where kappa is equal to 1 by rho is what? So when I put, that is 1 by R into L by A. So kappa becomes, I know that what is 1 by R? 1 by R is the G. So this equation I plug it here, where kappa is equal to G into L by A. So that is specific conductance equal to conductance into cell constant. So let us know the unit. So R always will have the unit of ohm. So the whole equation will have the unit of ohm, which means this L by A, if you take the unit, it will have length as the meter, area as the meter square. So the overall L by A will have the unit of meter inverse. So this specific resistance will have the unit of ohm meter. So upon cancelling this, we will get the ohm. For this, the unit will be, conductance unit is Siemens, and L by A will have the unit of Siemens meter inverse. So kappa's unit is Siemens meter inverse. So small s means it's a seconds, capital S means Siemens, it's a conductance, or we call it as a ohm inverse or mho. Okay. Next we'll move on to the next formula. So So next formula is the relationship between the specific conductance and the molar conductance. So first we know what is molar conductance. So the symbol is capital lambda m. We know that small lambda that we use it in the atomic structure as a wavelength, in the gaseous state as a mean free path, but in the electrochemistry we use this small lambda as the ionic conductance. The capital lambda refers the when the subscript comes as a m, it is molar conductance. When the subscript is eq, we call it as a equivalent conductance. So what is molar conductance? So that is very simple. If I take a 1 molar solution, if I fill it in the conductivity, if I dip the conductivity cell, whatever the conductance produced by the ions present in the 1 molar solution is known as the molar conductance. So which means the conductance produced by the ions present in the 1 molar solution is known as the molar conductance. So the formula is kappa by C, where C is in the molarity. So in turn I can write it as a kappa by molarity. So if I want to write it in terms of ml, so I have to put the volume, how much, so per liter, so I have to write the 1000. Okay, so this is the equation. So next similarly we can write the equivalent conductance. Equivalent conductance is capital lambda eq. So just you have to write the inversion of V, that is lambda, capital lambda, that is equal to kappa by normality of the solution into 1000. So what are the conductance produced by the ions present in the 1 normal solution is known as the equivalent conductance. So we know the molar conductance and the equivalent conductance, and we have to know the next formula known as Ostwald dilution law. Before that we have to know what is the degree of dissociation. Degree of dissociation. So degree of dissociation is nothing but DOD. The symbol is alpha. So this alpha is we can call it as a, if I take any electrolyte, if I put it in a water, so how much ion it can produce. So it is the number of ions dissociated divided by the total number of undissociated molecule present in the solution. So we can write it as the degree of dissociation is number of dissociated ions divided by total number of undissociated molecules. For example, if I take HCl, if I take there are 100 molecules, if I put it in a water, if it is 90 molecules are dissociated, only the 10 molecules are undissociated, which means 90 by 10. So then the degree of dissociation will be very high. Those the electrolytes which have the higher alpha value are known as the strong electrolytes, or the electrolytes which immediately forms the ions readily which dissociated form, they are known as the strong electrolytes. Or if the electrolytes they are poorly dissociates and form the lesser ions, they are known as the weak electrolytes. So this degree of dissociation has a very closer connection with the weak electrolytes because it explains the properties of the weak electrolytes. So the law was given by Ostwald dilution law, that will come next. So next we are moving on to the Ostwald dilution law. So I am just writing the formula, not the problems. So based on this we'll work out the formula in the future. So Ostwald dilution law. So as I told, it is only applicable for the weak electrolytes. Weak electrolytes means examples could be acetic acid, all the organic acids, acetic acid, formic acids, tartaric acid, and the base could be, the weak base is ammonium hydroxide. So this law is exclusively for the weak electrolytes. Okay, so what it is, suppose if I have the weak acid, for example I just name it as a HA, it is in the equilibrium, it dissociates and gives the H plus and A minus. So there is always a backward, it will combine and can form the undissociated molecule because it poorly dissociates and gives. But in the case of strong electrolytes, the reaction moves only in the forward direction, the backward direction is very less, but here it is equally probable. So we have to find out the what is called Ka. So we can write it as a Ka is equal to product concentration H plus and A minus divided by the undissociated acid molecule. So for that I can apply the ICF method. HA gives H plus and A minus. So initial there is only 1 mole and there are 0 moles of ions are produced. The changes could be the minus C alpha, here it is the plus alpha, here also plus alpha. The final will be 1 minus alpha, alpha, alpha. Upon multiplying with the concentration, I get C into 1 minus alpha, C alpha, C alpha. So this is the equilibrium concentration. So I have to just substitute this the corresponding concentration in this equation. If I put it, I'll get the C alpha into C alpha divided by C into 1 minus alpha. So totally it will become alpha square C square by C into 1 minus alpha. 1 C get cancels. So the final Ka will become alpha square C by 1 minus alpha. So this is the dissociation constant for the weak acid, the Ostwald dilution law. Similarly, we can write for the base as well. Where weak base, the dissociation constant for the weak base is again alpha square C by 1 minus alpha. Suppose the alpha value is very small comparing with the 1, so we can ignore the denominator. The Ka becomes alpha square C, here also Kb becomes alpha square C. So if in your calculation, if they give the Ka and the C, they are asking to find out the what is alpha, so you can write alpha is equal to root of Ka by C. Here also alpha is equal to root of Kb by C. So in turn, you can just tell the Ostwald dilution law. The degree of dissociation is inversely proportional to the square root of the concentration of the given weak electrolyte.